How do undersea cables get power over long distances? Imagine a giant underwater highway stretching across the ocean floor, carrying not just data but also electricity. That's what undersea cables do, connecting continents and islands with vital power. But how do they get the electricity from one place to another, especially over such vast distances? It's a fascinating process that involves special technology and careful engineering. Most long-distance undersea power cables use something called high-voltage direct current technology. High-voltage direct current means the electricity flows in one steady direction at very high voltages. This method is chosen because it loses less energy over hundreds of kilometers compared to alternating current, which switches direction many times a second. For example, a cable like the Viking Link, which runs about 760 kilometers between the United Kingdom and Denmark, can transmit around 1,400 megawatts of power using high-voltage direct current. That's enough to power hundreds of thousands of homes. The cables themselves are built with multiple layers. They have a core made of conductors that carry the high-voltage electricity. These conductors are usually made of copper or aluminum because they conduct electricity well. Around the core, there are insulation layers to prevent the electricity from escaping or causing damage. The cables are also armored with steel to protect them from physical harm, like anchors or fishing nets, and they are buried beneath the seabed for extra safety. Power is supplied at one end of the cable by a special station called a converter station. This station takes the regular alternating current from the land's power grid and converts it into high-voltage direct current for the underwater journey. When the electricity reaches the other end, another converter station changes it back into alternating current so it can be fed into the local power grid and used by homes and businesses. This conversion process is essential because our land-based power systems run on alternating current, but long-distance underwater transmission is more efficient with direct current. Some shorter undersea cables, usually less than 100 kilometers, still use high-voltage alternating current technology. But for longer distances, high-voltage direct current is the best choice because it reduces energy loss and makes the whole process more cost-effective. In addition to transmitting power, these cables often include tiny optical fibers embedded within them. These fibers are used for communication and monitoring. They help detect any issues or environmental changes, ensuring the cable stays safe and reliable over many years. So, in simple terms, undersea cables get power over long distances mainly through high-voltage direct current technology. The converter stations at each end handle the conversion between alternating and direct current, and the cables themselves are built to withstand the harsh ocean environment. This setup makes it possible to connect distant regions, support offshore energy projects, and keep the global network of power flowing smoothly.